This is the first lecture for week 3, and we're going to talk about T, or regular graphs, and degree distribution. First, let's recall what it means for a graph to be regular. A graph is R regular if every vertex has degree R. So, for example, a cycle is 2 R regular. Peterson's graph below is 3 regular. And a complete bipartite with 4 vertices in each partite set is 4 regular. There are different ways that we can describe the degree of a vertex. So let's look at the 3 different ways that we can describe the degree of a vertex, and then we'll generalize the degree. So you can think of the degree of a vertex V as the number of edges that are incident to V. Or you can say it's the number of vertices adjacent to V. Or you can say it's the cardinality of the neighborhood of V, where the neighborhood is the set of all adjacencies. So to generalize the definition, we could say that the T degree is the number of edges incident to a set of vertices of size T. So when T is 1, you have a single vertex, and you're back to the original definition. So we could say it's the number of vertices adjacent to a set of vertices of size T, or it's the cardinality of the neighborhood of a set of vertices of size T. Now, we want to make the set an independent set. That is, there are no edges in the set of size T. This is because we do not want any vertex to be in its own neighborhood, in the same way as we don't want a loop in a graph when we're looking at the degree. So now let's generalize the idea of regular. A graph is said to be TR regular if every collection of T independent vertices is collectively adjacent to exactly R vertices. That is, the cardinality of the neighborhood of a set of T independent vertices is always R. So let's look at Peterson's graph again. We said that Peterson's graph is 3 regular. We now claim that it's also 2, 5 regular. Since we're saying 2, 5, in particular since we're saying 2, we mean if we take any independent pair, that they are collectively adjacent to exactly 5. So I've circled an independent pair and looked at its neighborhood. Every vertex in the neighborhood is adjacent to at least one of the circled vertices. And as we've checked them off, we can see that there are 5 vertices in the neighborhood of that pair. My claim is it doesn't matter what pair you pick, as long as they're independent, as long as they're not adjacent to each other, then collectively they will always be adjacent to exactly 5. So in that sense, we've generalized regularity. So Peterson's graph is 3 regular. It is also 2, 5 regular. If we change the size of T and ask is it TR regular, then that answer is no. Let's look at another example where we have a 2R regular graph, a very simple example. We have a 2, 2 regular graph, because if you take an independent pair, then they are collectively adjacent to 2 vertices. Now here's another example of a graph that's 2R regular. In particular, it's 2, 10 regular. If you look at the vertices on the left, there is a complete graph on 6 vertices, and on the right, you have 4 copies of a K3, or 4 triangles, and then you have connecting edges between these. The vertices that are red are the connecting edges, and the vertices on the left are adjacent to all of the vertices on the right. Since the vertices on the left are adjacent to all the vertices on the right, and they're also adjacent to each other because it's a K6, the vertices on the left are of degree n-1. That is, they cover everything. So if I want to pick an independent pair, I can't use one of the vertices on the left. I have to choose a pair from the vertices on the right. which means I have to pick a vertex from one of the triangles and then go to a different triangle and pick another vertex. So if I pick 2 vertices in that way, I will always cover the 6 on the left, plus they will each cover an additional 2 vertices on the right. So 6, 2, and 2, I will always have a neighborhood set that's exactly 10 for whatever pair I pick. And that's why this is a 2, 10 regular graph. We want to denote this using notation like we see on the left. This is a K6 plus 4 copies of a K3. In particular, this is called the join of 2 graphs. The join of 2 graphs is the graph you obtain when you connect every vertex in one of the graphs to all of the vertices in the other graph. So the red edges are what we get when we join a K6 to 4 copies of a K3. So here is another example. In this case, we've joined a K3 to 3 copies of a K2. And the claim is that this is a 2-5 regular graph. So if you pick 2 independent vertices, you'll cover the triangle, plus an additional vertex below. So it will always be exactly 5. Now, is this kind of graph a small world graph? What is the clustering coefficient of this graph? Notice that the vertices below in the K2, their neighborhoods each induce a complete graph. So the ratio of the number of edges in the induced neighborhood over the number of possible edges in the induced neighborhood is exactly 1, because all the edges that could be there are there. Now, what about the clustering coefficient of each of the vertices in the triangle? Recall, for the clustering coefficient of the graph, we add the clustering coefficient of all of the vertices and then divide by the total number of vertices, so we're just taking the average. So what is the average in this case? Well, so far, we know that there are 6 vertices from below whose clustering coefficient is 1, so we've written this down below. And there are 3 vertices whose clustering coefficient we haven't determined yet. And then we're going to add that up and divide by 9. So what is the clustering coefficient of the vertices in the triangle? If we choose one, its neighborhood is the entire graph except for itself. So the total possible number of edges that we could have is 8, choose 2. Now, to count the edges in the induced neighborhood of a single vertex from the triangle, we have 4 edges, the 3 that are below and the 1 that's in the triangle, plus the edges that run between the K3 and the edges below. And since there are 2 vertices other than the one whose coefficient we're considering, and they're each adjacent to 6 below, I claim there are 12 edges in the induced neighborhood running from the top to below. So the total number of edges is 12 plus 4, or 16, over 8 choose 2, which, doing the arithmetic, will reduce down to 4 over 7. So we come back up. Now we know what the clustering coefficient is of each of the 3 vertices in the triangle above. So we put in 4 over 7, and our clustering coefficient is very high. 0.857 is very high for a network. Remember, the clustering coefficient ranges from 0 to 1, with the complete graph being the only graph that has clustering coefficient 1. We'll talk some more about what we mean by sufficiently high when we look at different models of small world graphs. But clearly this is sufficiently high since it's way more than a half. What we're interested in now is larger graphs, because in the real world, the networks that we will be studying are very, very large networks. And they tend to grow over time. So we want to understand what happens to our graph as the number of vertices grows. So this example that we've been looking at is a good way to introduce that concept. How would we grow this graph? One way that we could do it is leave the 3 fixed. That is, there's a triangle on top. Leave the edges below fixed, but add the number of edges that we have in the graph. That is, this is now the join of a K3 plus 3 K2s. What if we say it's a K3 plus M K2s for whatever M is, where M is the number of K2s below? Then we can increase M. As we increase M, that naturally increases N, the number of vertices in the graph. So if we want to increase, as I was saying, the size of the graph, the general form is a KS plus M copies of a KP. In the previous example, S was 3, P was 2. But in general, if we're looking at a KS plus M copies of a KP, what we want to do is grow the graph by increasing M. It's important to note that what we're doing is let S and P be fixed integers. And if S and P are fixed, M is tending towards infinity. And then we want to still be able to say what is the clustering coefficient as M grows, or what is the clustering coefficient, noting that S and P are fixed. The degree sequence of what we looked at so far is the vertices in the triangle have degree 8. So we would have 8, 8, 8. And then the vertices down below have degree 4. So it would jump to 4, 8, 8, 8, and then 6 4s. But the general degree sequence then would be n minus 1, n minus 1, n minus 1. There would always be 3 since there are 3 vertices on top. But the number of vertices below would grow by pairs, and so we would have a long string of 4s. Now, what happens as far as the small world nature of this graph? Notice that even though we're adding a lot of edges into the bottom, the degree of each of the vertices in the edges below doesn't change. It's still, in each case, 4. And as M grows, then 4 becomes a relatively small number. So you would have a lot of vertices of relatively low degree, and then you would have a small collection of vertices of very high degree, which would suffice to be your hub. So the nature of this graph is a classic small world, in that you have a collection of vertices of high degree, most of the vertices of low degree. The average path length is low, and intuitively you can see for this graph, the average path length would lie between 1 and 2, so that's extremely low. Because if they're in the same edge, the path length is just 1. If I want to go from one edge to another edge from the vertices below, I can go up to the triangle and then back down. So the highest you would ever have to go is 2. So we're building an extremely small world graph. So if we increase the number of edges by M, what is the clustering coefficient? Now we did it in the case where M was equal to 3. So some of the arithmetic is still the same. The vertices of degree n minus 1, we still need to count the total number of edges over n minus 1 choose 2, because they are adjacent to everything. There are m plus 1 edges if you count the m edges below and the 1 in the triangle. Plus, now we have to count the edges running from the triangle to below. So each vertex is of degree 2m, and then there are 2 of them in the induced neighborhood. This gives us, doing the arithmetic, in the top 5m plus 1. Now below, I want everything in terms of m. We have n minus 1 choose 2, but what is n? It's the total number of vertices minus 1. And the total number of vertices is twice m plus 3, so minus 1. So expressing it all in terms of m, we come up with the ratio of the clustering coefficient for the vertices in the triangle for each one is 10m plus 2 over 2m plus 2 times 2m plus 1. Now, if we look at that, just that expression there, what happens is m tends to infinity. What does that ratio tend to? Now, to find the average, we'll take this back into our equation where we're going to add the clustering coefficient of all of the vertices in the graph and divide by n. I'm not going to finish this. I think we've taken it most of the way, but it looks like a good homework problem to finish this out. So this was the first example we had where it was 210 regular. And we know that this is a K6, as it was written, is a K6 plus 4 copies of a K3. Again, we can let the number of copies of the K3 increase in order to grow the graph. And then once again ask, in terms of m, just the general case, what is the clustering coefficient of this graph? So we have defined what we call a TR regular graph, where every T independent vertices are collectively adjacent to exactly R. And the examples that we used was when T is equal to 2. We looked at independent pairs. We've looked at examples of how a network can grow, that is, the number of vertices can tend to infinity. And we've looked at what this means in the setting of small world graphs.